to understand the equation. I didn't have to understand, like, because sometimes, I just had to apply it. I had to be able to apply the equation, but I didn't truly, because some of the things in calculus and differential equations didn't make sense at first, but I'm like, okay, don't worry about it. Just remember, all you have to do is solve the problem, be able to apply those equations to solve. And then what happened over time was the understanding came to me, later. Sometimes it didn't come while the professor was explaining whatever it was.
Yeah. Well, one thing along those lines that I noticed is that, I got a lot of stuff out of courses, but never 100%. And then when you actually start to teach it is when the circle really comes around, and then it's like, oh, now I get it. And, you've always been able to apply it, but you didn't quite know why it worked or, what else. And so when you start to teach it, that's really when it's like, now finally, after, how many years, I kind of get this now. And so there's definitely an ongoing learning process. You might got to see several things multiple times before it kind of really clicks, right? Before you really master a subject. So
I agree. What's your favorite class to teach, Paul?
I think mechanics for materials is really one of my favorite ones to teach, because it's one of the first classes where you really get to sort of do something fun with the material you've been learning, like calculus and statics and stuff. And so really, once you get to mechanics and materials, you really start building things. You really say, oh, now I get why I learned all this. Now I can build a structure. And so start being creative with it. And I kind of like that.
No, that's great. All right, now I'm making sure I can share screen. So I'm going to get into share screen mode for an on-time start. So give me a moment. I'm at work, audience, because we had a massive power outage in Houghton with over 1,500 people without power, believe it or not, which is, what would you say? That's like 10% of town or something like that?
Give or take.
Something like that. Yeah. No, all right, let me do, oops. Now what did I do? There we go. All right. Well, and while we're, while I'm at my office, you know what I should do? I should stop sharing and show you the view out my window before we get officially started. All right, you guys got to see this. The fall colors are turning. This is the view outside my office window. Can you see the bank over there? Yep. Just beginning to turn, and the beautiful view. I'm at work again because the big power outage, which I can't explain why there was a power outage. All right, so I need this. Now I can't share screen properly. Click to exit full screen. There we go. All right, so welcome everybody to Husky Bites, season 6, episode 2. My name is Janet Callahan, and I am Dean of the College of Engineering at Michigan Tech. And like I said, this is Husky Bites season 6. So this is a free webinar series that you are welcome to join as many times as you want to. You can also watch recordings if you wish, and you can also join us on Facebook live stream by just going to this particular web address or searching for it. This was the power outage we had. When I looked there, I immediately sent Paul an email saying, if you have power where you are, stay where you are. But since then, the power has been restored. And I'm sharing, we shared sunflower seeds with alumni, and with some of the alumni, I sent them my own sunflower seeds, which were mammoths. And so this is Dan's, how tall his mammoth sunflowers got. And you can see they've the weight of the sunflower at the top bends it down. And so Dan had to prop this one up with guy wires, and they exceeded the height of the stakes. And you can see they completely outcompeted the tomatoes for light. So nice work, Dan, with your garden. This is these are all of the topics we'll be covering this fall, and it ranges. We started last week with rails, and we'll end with the beautiful geology of the Keweenaw. And this evening, we're going to be hearing a little bit about the Multiplanetary Innovation Enterprise. And so many of you out there are alumni, and if you are interested in continuing to learn beyond Husky Bites, I just wanted to point out that we have all kinds of online graduate certificates. And so what's a certificate? It's a group of usually 3 classes, three credit graduate classes. So you just take one in the fall, one in the spring, one the following fall, and you've earned a graduate certificate. It's credential. It'll show up on your transcript, and then you can take a break and you can come back and to get another certificate, and you can stack them toward a master's degree. And typically for a master's degree by coursework alone, it's 30 credits. So you can see that taking 3 of these gets you to about 27 credits, and then it's just one more class for a master's degree. So I wanted to make sure you knew about these opportunities. And this is just within the College of Engineering. There's even more in the College of Computing and so forth. Next week, our speaker will be Mike Roggeman, who is in the Department of Electrical and Computer Engineering. And feel free to join us early for conversation and find out what we did that week and what the weather's been doing and things like that. Thank you, everyone, for joining us. And I'm going to now stop sharing while Paul, or whoever's in charge of the slide, starts sharing. And I'm going to introduce Paul and then turn it over to you. So Dr. Paul van Susante, I hope I said that right, came to us originally after having been born in the Netherlands. He earned his one of his 2 master's degrees from Delft University, which is a very excellent university. He then came to the US and attended Colorado School of Mines and also taught there over a period of years. He was a NASA faculty fellow in about 2011. He's a terrific teacher, and teaching was his first passion, but we couldn't keep him from doing research. And so, and he's very talented, and he's very interested in space, and so and extreme environments. And with that, I'm going to just turn it over because I know you have an intro slide about yourself too, Paul, and I know you'll introduce the students.
All right, thank you very much, Janet. So, yeah, my name is Paul van Susante. I'm assistant professor since 3 years. And today we're going to talk about the Multiplanetary Innovation Enterprise. And I have 3 students with me today, Brenda, Gabe, and Parker, who is going to talk each about their different projects that we have in the Innovation Enterprise. But before we do that, I'm going to introduce a little bit about the lab that I founded, the Planetary Surface Technology Development Lab, of which the mine enterprise closely collaborates with. So just a little bit of background information on myself. I have a wife, or I should say she has a husband, me. Anyway, we're married 17 years. And I have we have a son, Xander, who's now 8 years old. Hard to believe that he's already 8. And in my free time, even though sometimes it is scarce, I like to do a lot of outdoor activities. And you can see some of those pictured down here. One of the things we love to do is go out here in Keweenaw and enjoy things like the beach. And then sometimes we get treated to northern lights here. So this was a couple of weeks back, a picture on Bleacher, or on the, what's it called? Not McLean State Park, but the other side. Anyway, lots of cool stuff to do here. And we really enjoy living here. Dr. Callahan already explained a little bit about my journey here, so I have a little bit more of that here. So I was born in the Netherlands. I got my bachelor's and master's degree in civil engineering from Delft University of Technology. I did an internship at the European Space Agency because I was always very interested in space. Then I got invited to the Colorado School of Mines to sort of continue my space work there. I got another master's degree and a PhD in engineering systems. And then also, like Dr. Janet mentioned, a NASA faculty fellowship in 2010, where I spent 2 months at Kennedy Space Center working with what they call now swamp works, figuring out landing pads for the lunar surface. Then in 2012, I came here First, it was a lecture, then a senior lecture, and then I did more and more research, and I became an assistant professor in 2019, where I founded the Planetary Surface Technology Development Lab. And so my goal has always been to help humanity establish permanent presence off of Earth, on the moon, and improve life on Earth while doing so. Quick poll question for you people out there. How long is a lunar day? See here some options, and you might want to play around with that. And so is it A, the same as 1 Earth day, B, 14 Earth days, C, very oddly specific, 27 Earth days, 7 hours, 43 minutes, and 12 seconds, or D, 29 Earth days, 12 hours, 44 minutes, and 3 seconds, or E, none of the above? Kind of curious what you're all thinking here.
Well, and of course, when there's two specific ones right around the same number, I would say that it's going to be either C or D. And
now, those are interesting test strategies, but I anticipated that. So watch out.
All right. Well, you've got very low choices on A and B, lots of choices on C, and you've got actually almost 20 people who say none of the above. And I'm starting to suspect that to be true.
Yeah. Well, the actual answer is D, actually, but it depends a little bit on how you define it. So it takes 29 days, 12 hours, 44 minutes, and 3 seconds to be back to the same phase. In other words, the same appearance from Earth. And so that's typically considered the synodic month. But if you want it to be in the same position over Earth, then it is 27 Earth days, 7 hours, 42 minutes, 12 seconds. So just an interesting fact there.
I think you skunked us, because most, it's pretty hard to skunk our Husky Bites audience. They chose C, but the answer was D.
Depends on your definition. Theoretically, they could both be true.
Yeah.
So anyway, let's continue. So what do we do? Well, just to put a little bit in context here. So NASA wants to go back to the moon, and not just NASA, but a lot of people around the world, a lot of organizations. And to that effect, NASA has started what's called the Artemis mission. So Artemis is the twin sister of Apollo. And so this is sort of the sequel, if you will, to the Apollo missions. But now the goal is to go back in a sustainable fashion and create permanent presence on the lunar surface. And so on the side of that, there is a lot of commercial activities going on in the space economy. And so lots of investment happening there. But the key here is that we need to develop this technology to support using local materials to do this sustainable. And sustainable, I don't mean that in a green sense, like we use it here on Earth. Sustainable here means that we can do more with the same budget in a way. And so sustainable means over the long term within NASA's budget in a way. And so to do that, we need to bring less liquids and like I call it dumb materials, but we want to bring scientists and materials and things that are value added. And that means not bringing things like water or liquids or fuel, but we want to be able to make those things locally. And so using the local materials is really what we're trying to do. Right? And so to be able to do that, we need lots of power. We need to be able to mine the local materials. We need to then process it into useful things, and then we can actually make things out of that, whether that's tools or bricks or something else. And then if we want to stay there long term, we also need to be able to grow things. So agriculture is also another factor. But the key is to minimize anything we bring from Earth and use as many local resources as we can, whether that's on the moon and Mars and other places as well. And so NASA is doing this in partnership with the European or with the commercial sector. And so to be able to get the commercial sector interested, it means there needs to be able to be a profit. And so we need to be able to find something that we can recover, that we can mine. Then we need to have the technology to mine it. But then you also need a customer that's willing to pay for it, right? And so those three things need to be all present before you can have really a commercial space industry, basically. And then current rockets are being developed to transport lots of stuff to the moon and other places. And so just as a reference, I always like to show that these rockets are not small. And the reference here is the meme building. That's the red line indicated on the bottom right. And so these rockets are real things. They're not just drawings. You can see the pictures just to the left here, the real rockets that are currently being put together to start flying here this year. Now, what do we do? Well, our lab, the Planetary Surface Technology Development Lab, focuses on increasing the technology maturity, right? So in other words, from idea, we prototype it, we test it, we build it until it's basically ready to go to space. And what that call is technology readiness level 6. And at that point, the risks are low enough for NASA to adopt that technology potentially to actually use on space missions. And you can see some of our lab facilities here. Some recent accomplishments is we won several competitions for NASA, some What's on the Moon challenge. You can see NASA Administrator Jim Bridenstine handing us the prize, unfortunately virtually at the time because it was part of during the COVID shutdown. But anyway, so we were very successful in this, and we only just recently were invited to phase 2, level 2 of the What's on the Moon challenge because we also were one of the 7 winners of the phase 2 level 1 to continue that. Now, my lab does a lot of research.
Congratulations, and audience out there, it's a really big deal to win these.
Yeah, so this is open to literally everyone to compete in these, and so to be selected as one of 7 in this case out of, I think there were 30 applications of universities and companies and anyone out there to do this is a pretty big deal. So the students team that works on that works really hard, so thank you. But yeah, so that's only part of the things that we do in my lab. So this is a complicated diagram, but it shows basically that we have lots of funded grants, about $4 million in the past 3 years. We have some test contracts that are companies that come here to do testing specifically in our facilities that are unique in the world. And we also do these competitions, and we have funded research grants at the top here. But in addition to that, and that's our topic for today mostly, is the Multidisciplinary Innovation Enterprise, where we currently have about 50 students currently working on 3 projects that are related to extreme environment testing, such as the trencher and the lunar conditions, Lunabotics for lunar excavation and autonomy, and then the underwater robotic vehicle called Diver. Anyway, so those 50 students are organized in an enterprise, and this is last year's organizing chart. So one project was ended last year, externally sponsored one, and this year we have 50 students. We've grown 10 students in the past year. Just to cap, right, PSTL and mine, we are currently working on developing and getting that technology to level 6, where NASA might adopt it for actual space missions. And then our goal is to actually get on a space mission that goes to the lunar surface. We would like to have a Michigan Tech mission to the moon. That is our goal. Because we are part of the Artemis generation, or we do the Artemis missions. We help NASA achieve their goals, with in the end the goal of becoming essentially self-sustaining on the lunar or Martian surface, and have permanents live permanently out of Earth, off of Earth, basically. And with that, I want to introduce Deborah, who's going to talk about the Lunabotics team. Deborah, all yours.
All right, yeah. So I'm Brenda. I'm a 4th year electrical engineering here at Michigan Tech. I'm the electrical subsystem team lead for the Lunabotics team. So right here on our cover slide, you can kind of see our little logo after Huskies. And on the left side, we have a photo of our team who went to the competition last year. And the right is the Lunabotics robot. His name is Murphy. But to give you a little background on what Lunabotics is it's a competition sponsored by NASA, where we are targeted with building a robot over the course of 1 year to complete a specific task. And in this past year, the task was excavation. On the next slide, we have a video. You can kind of see the video works, hopefully, where we are traversing across the playing field from, all right, well, anyway, part of it, what we have to do is we have to traverse across a field laid out, go around obstacles over divots and such, and go into an excavation field. On the right side, you can see the map that I'm describing. Dig 30 centimeters under the surface, and then collect samples of icy regolith is what we are looking for, and then bring it back to the hopper base down here at the south as like a beacon. What we are digging through is lunar regolith, which is a simulant of the kind of the ground soil type material, not actually soil you would see on the moon. And we are trying to collect specifically gravel samples that would possibly contain ice that could be used for various uses by astronauts on the moon. Next slide, please. Now, so how do we go about building a robot? So how we're going to do this is we use a system engineering process with the Lunabotics team, where we kind of start with a broad overview here on the left side, go over concept operation, requirements architecture, detailed design. And then once we have all of those things planned out, we'll go down to the implementation. The implementation stage is where we spend the bulk of our time, which would be building prototypes, simulations and things like that. And then we'd go back up, testing, verification, system verification, validation, operation, and maintenance. And we kind of repeat this process until we get the goals we're trying to achieve. Specifically with the Lunabotics competition, we are trying to, last year's competition, we were trying to get 1 kilogram of regolith sampled, bring back within a 15-minute time frame. This year, the competition is changing a little bit, and it's going down to a 0.5 kilogram icy regolith sample in a 10-minute time frame instead. Next slide. Yeah, so a quick question is, what are some of the characteristics of lunar regolith simulant? Just a reminder, lunar regolith is kind of the moon dust material that NASA has us use in the competition to try to give as close as we can to behaving on the moon as possible.
And so the choices we have are that it's semiconductive.
Yeah, it's semiconductive. It has smooth edges. It's flammable. All of the above are true, or none of the above are true.
I don't know. This is another really hard one. And the audience doesn't really know either, but quite a lot of them are going for all of the above and also for none of the above. So this is truly a really, really hard question.
Yeah.
With no intuition on it.
Well, Brenda, maybe you can explain a little bit maybe on how it was formed. That gives them a clue.
Oh, yeah. So I don't know a whole ton about how it was formed, but I know some of the initial designs initial materials used to make regolith was done with a basaltic ash and glass. And so it's made of composite material. And so that being said, it is not semiconductive. I don't know who's in charge of taking results, but I don't know if you'd like me to do that now, but I can do that. Yeah, there we go. But yeah, so it's not semiconductive. Just because it's made of composite material. But the interesting thing about the lunar regolith is that rather than like sand or like glass we have down here on Earth that has smooth edges, lunar regolith actually has kind of sharp edges on it. And so I don't know exactly how this is done. Paul, if you have more insight on this, feel free to share. And it's also not flammable because again, it's made of composite material. And so the correct answer to this is none of the above.
Yeah, I'd be happy to talk more about that, but that's probably a lecture in itself. But yeah. But we can answer that question at the end, perhaps.
For sure. But the interesting thing about this is having the sharp edges means it behaves differently than we would as with sand or soil here on Earth. Because it has those sharp edges, it tends to clump together, and that can cause a lot of issues if it were to get into any type of gears or chains and things like that, just because it'll start clumping together and causing wear and tear on those components. So tap it again, I think it'll show you the answer here. In a second. And then if you tap it one more time, I'll go to the next slide. There we go. Yeah. And so knowing those as well as what our competition boundaries are in terms of the 15 minutes and trying to dig 15 minutes or get a kilogram of icy regolith in 15 minutes competition time, we have a lot of considerations we need to have in our design. Those being the dust proofing for that regolith that we just discussed, making sure we have enough power to last those 15 minutes. And then along with that, there's additional restraints that NASA gave us, such as the volume of the robot, the mass of our robot, our ability to move and navigate the obstacles in the course. Certain materials won't be safe for space, so making sure we can meet those goals. Cost, other goals within our own team that we'd like to achieve. And then this year, we're also going to be considering what we learned from last year, giving us a bunch of system requirements that you can kind of see our overviews on the left. Our big requirements that we set for ourselves are excavation, which is kind of telling us that we need to excavate regolith and icy regolith simulant with the particle diameter of 2 centimeters. That's kind of being our goal masses and goal material that NASA wants us to collect for the competition. The deposition, which is depositing the regolith that we collect back to that home base. Traversal, ability to go around the obstacles. Autonomy, which is making the robot able to be autonomous, navigate the course and complete tasks on its own. And communication objective, making sure to communicate back to those of us running the robot at the quote unquote home base. Next slide. And so with that, some difficulties we've had in design in the past is the electrical system had had issues with wire management and port connections, just because working with soldering irons and they try and make the system closed off. You try to make it everything as tight as possible so you don't have too much wiring that can get caught on other systems and or any dust that can get in and interfere with the connections. The chassis system we had had issues with turning and getting traction. The regolith is kind of like sand in the sense that you will spin in place if you're don't have the right kind of wheels. And so we had to work to make sure we were able to navigate through those things. Two more systems we have are the hopper system and the excavation system. Hopper system is where we collected all of the regolith we were mining, and then we would try to sift it out. So that way we would only be left with the icy regolith gravel that we are trying to obtain, and then working on pouring it into the hopper system, or pouring it back into the home base, which took a while to deposit. And then excavation, which is the digging itself. And we had the issue where buckets were breaking off from the excavation system that you can see there in the photo. Next slide. Yeah, and so some solutions we created for those based on experiences from last year that we're hoping to implement this year and or had the chance to try implementing the end of last year is we're going to be trying new products for our ports and budgeting in space, as in like volume space at the beginning of our project for electrical system, just to make sure that we're not going to have any snags that happen, and also being able to get more different hardware, better products, and hopefully make sure that those work and get checking them ahead of time. Hopper system, we're going to get vibration work and sifting systems because, as mentioned, the regolith will stick together, and by shaking it, we can hopefully loosen some of those connections the regolith makes within itself and kind of filter out all the material we don't want. The chassis system will be going with a square-shaped wheelbase for best mobility and turning, larger wheels and fins, and frequent gear checks to make sure that the system isn't being worn down by the regolith getting caught in anywhere. And in the excavation system, we had the issue with the buckets breaking off. And so we're going to, across all systems, we're going to do no more 3D printed parts in the future, going back to that material system requirements we set up, and then also including sensors to monitor the system so we know if we hit any large underground obstacles, we don't try to push through it and break off something, and make sure we're not going too far down, putting stress on the system. Yeah, and so if you want to look and continue hearing about what the Lunabotics team is doing, our Husky team is doing here at Michigan Tech, we have a website, the Mine website, that I believe will be put on the end of the presentation. But if you want to help Lunabotics specifically, we are fundraising for our project. We are fundraising through Superior Ideas, and so you can click there where you can read more about what we're doing, what we're working on right now, and then also help sponsor our project and get our name on a t-shirt, a sticker on a robot, or cool things like that.
And let me just add that counts as a Michigan Tech donation, so you get a receipt for it and everything. And so I'm just going to read off that website. So it's www.superiorideas.org/project/lunabotics-rover.
Yeah, it's a pretty cool thing. This year, the competition is going to be held at Alabama University rather than NASA, just because they're trying to change up the competition for next year. And then, but this previous year, we did really well. We were one of the few teams, one of 10 out of 50 teams that actually manage in collecting regolith at all and bring it back to the home base to turn it into the hopper system. So that was really cool. So we did not win the competition overall, but we did really well, and we're very proud of what we accomplished and are hoping to do better this year.
Nice work.
All right. All right, cool. I guess now it's Parker's turn to talk about the Trencher project.
Yep. So my name is Parker Bradshaw. I'm a third-year mechanical engineering major. This is the Lunar Trencher project. So similar to Lunabotics in that we're doing excavation, but different in that we operate in a vacuum environment instead of an atmospheric environment. Next slide. So here's a little box taken from one of Paul's slides earlier, what we need to do here on Earth to prove that this in situ resource utilization on the moon is possible. We are focused on developing the excavation technology in order to extract all the valuable resources that are in the regolith, and also just to get bulk material for building things like landing pads, berms, roads, all the civil engineering stuff you need to reinvent in order to do on the moon. So what the trencher is, a trencher is a series of buckets on a actual chain that spins around in a big oval shape. You shove it down into the ground and it continuously excavates the regolith out of the ground and into your robot collection system or whatever else you have there. Next slide is the poll question. This is our last moon-related poll question. What's the hardest part of operating on the moon? So this means what's the hardest part of getting astronauts on the moon to do stuff over a long period of time? First, the vacuum of space. There's no air up there, obviously. Second is getting food and water. So either shipping food and water there or getting it in situ. The extreme temperatures in the daytime, it's extremely hot. In the nighttime, it's extremely cold. And that varies where you are on the moon as well. And the last challenge, lunar regolith.
This is the toughest questions I've ever seen. This it's very impressive. So the audience is again befuddled. I'm leaning to the extreme temperatures as well.
And this answer is based on a report that NASA released about this exact topic. What would be the #1 challenge that we face going to the moon?
Close. Extreme temperature and lunar dust are almost equal.
Yeah. Well, all right. Tell us the answer.
Yeah. So the answer is, if you go to the next slide, lunar dust. The regolith is a huge challenge. You can see here in the Apollo missions, they obviously had a set amount of time that the missions were planned for, but one of the main things that was limiting them further was the dust getting in all their stuff. So it's a picture of the moon car that they had and their spacesuit, which just got totally covered in regolith. They probably would not have been able to do any more EVA operations beyond what they did. There's a little picture of the regolith that we make in-house in the bottom right, and a little sample of what it does to mechanical systems in the top right. That's a microscope picture of a piece of metal, a wear surface. You can go to the next slide. So here's what the trencher project is in the nitty-gritty. We have our giant vacuum chamber, which we operate in. It's a dusty thermal vacuum chamber, which is a capability that's among universities almost unique to Michigan Tech. Very few other people have this. So we can make a bunch of dust in there. We can bring it up and down to lunar temperatures. The trencher goes on a cart that's slid into and out of this vacuum chamber. It's a big cart full of dirt, basically, or very much not dirt, regolith. And a lunar trencher rotates, gets placed into the dirt or the regolith, and traverses across the vacuum chamber, excavating the whole time. On the next slide, I don't believe this video is working, but oh, it is. Look at that. So here's a video of the testing that we're doing in there. So you can see our bucket chain is moving around. It's scooping up regolith from the bottom of the bin, carrying it up into a chute, and the chute brings it over to the side where it is collected. On the moon, this would be put into something like a molten regolith electrolysis reactor or something like that, or used for some purpose. We are just collecting it and weighing it to see what our excavation rate was over the duration of the test. Next slide. Here's our test results. So the main thing that we're getting out of these tests were done last year. Main thing we're getting out of them is the mass flow rate. We measure all that dust that we got out of it, and the power consumption that we use. So we do real-time power monitoring of all of the systems. There's only 2 systems, the system that moves it back and forth, and the actual rotation of the buckets. Next slide. So those 2 things that we got, the regolith excavation rate and the power efficiency, were enough for us to publish a conference paper or 2 last year, and that was presented at a conference, a real professional conference by some of the grad students in the PSTDL lab. This year, we want to build on that and publish a proper journal paper, which is a much lengthened version of the conference paper. And we want to specifically talk about the wear of the system. So as much as we are exploring excavation technologies on the moon, what we're really exploring is how to make mechanical systems work on the moon in all of that dust. So stuff like the 3-body wear of the pins inside of the chains, the 2-body wear of the bucket blades scooping out the regolith. So in order to do that wear testing, what we need to do is longer duration tests, because that video you saw was the entirety of the testing in one vacuum cycle, which takes about a day. So our future plans are to put the trencher on a vertical stage in the vacuum chamber. So it can, once that video is over, it can go back to the start, go down and take another pass. And that gets us much more time, gets us much more significant results. We are also trying to put it onto this hoplite rover you see at the bottom, put the whole trencher on the front of that, and we will run it outdoors for very long amounts of time in a closest thing we can get to regolith that's just out there in the world, the Keweenaw stamp sands. And all of this is so that we can publish this journal paper, which will inform future NASA machines that they're building to put on the moon. That's all I have.
I think it's a really creative use of stamp sands.
Then we have our last speaker here. Thanks, Parker. Gabe, Allis is the last speaker here, who's going to talk about the last project, the Diver project.
Yeah, thank you, Paul. Yeah, so as Paul said, I'm Gabe Allis. I'm a 4th-year electrical engineering student here at Mine. I'm a co-lead of the Diver project, so I'm excited to tell you about it. Next slide. Yeah, so I'm right in to give you a little background on our project. The renewable energy industry is kind of the backdrop of our project because it has a problem. It's not always sunny or windy. Solar panels or wind farms are never going to be operating at peak efficiency. And we don't have a good place to store energy as it is. So you can see a picture on the right of the pumped hydro plant at Ludington, Michigan. And the whole idea is during times of energy surplus, so say at noon on a relatively cool day, the energy produced by solar farms may exceed power demand by a lot. And so what they can do at Ludington is they can pump water up into this huge reservoir and then drain it through a turbine during times of energy deficit later in the day. As you can imagine, these are very expensive to build, and there are very limited sites where you can make one of these things. A lot of land area. There's also lithium ion, which are also expensive to build. And there's a limited number of cycles you can run a lithium ion battery through before they're worn out. You have to replace them. So now we can go to the next slide. Yeah. One idea that's being explored right now is called pumped underground hydropower storage, or PUSH. And as you can see in the picture on the right, an artist rendering of a PUSH facility, the idea is you could take a flooded mine shaft and basically do the same thing that they're doing in Ludington right now. So some of the advantages to this idea is that it's there are hundreds of potential sites for flooded mines that could be converted into PUSH facilities, maybe. They're less expensive. You don't have to build a reservoir. You're not making an unsightly structure, so there's less regulatory red tape there. Kind of going backwards in my bullet points. It's impactful to the industry, and it's large-scale energy storage potentially. Some of the problems with this idea is there is a structural component to an abandoned mine that's been there for centuries. If you take the water and change the setup of the mine there's a risk of collapse. So someone or something has to go down into the mine to determine whether or not it's viable for conversion if it's structurally sound. Next slide. So this is where my team comes in. DIVER stands for Deep Investigation Vehicle for Energy Resources, and we aim to design and build a robot for the exploration of flooded mine shafts, specifically for their evaluation of whether or not they're suitable for conversion into PUSH facilities. Of For our design case, we're looking at Quincy Mine, which is a mine right across the Portage River, or 15 minutes from campus, if you're not familiar. And the reason we chose this mine is because we have a lot of information on it. We were able to find a lot in the library archives. So I have a poll question for you guys in the next slide. To what depth is Quincy Mine flooded? What do you guys think? Is it 400 feet, 6,000 feet, 52,000 feet, or 41 million feet?
I think you asked a question that they know the answer to. So many people are guessing B, 6,000 feet, or just over a mile deep. And they're pretty sure. It's like
Pretty sure.
78%.
I'm waiting to see if anybody selects D.
41,000 million feet. No,
Looks
no.
like not. Okay. All right. That's the diameter of the Earth. So that's good that nobody selected that one. Yeah, no, the answer is 6,000 feet. So just over a mile. And if we go to the next slide, with that in mind, we can do a quick calculation. Yeah, so I did it earlier. So it comes out to around, I think, of a lower bound of 41,000 watt hours, which for context, a typical car battery has like 700 watt hours. So that's a rough lower bound estimate that we can make based on that head difference. Yeah, so we can see in this slide some other specifications for this design case. So we know that the main shaft is at an angle. So that means 8,000 foot minimum to reach the bottom. We know that it's probably going to be around 90 degrees Fahrenheit near the bottom of the mine because water gets hotter as you get near the mantle. We're going to need a sensory array because the whole point of this mission is to collect data on the mine. So we're going to be monitoring the temperature of the water as we go down. This will be able to tell us whether or not there's water inflow from an external source into the mine, if there's truly what we expect to see in water temperature there. We're also going to be sampling the water at various depths to get an idea of the alkalinity or the iron content, for example, of the mine. And we'll be doing all this without GPS. So we're going to be having to do real-time mapping using Kalman filters, Doppler velocity logs. That's something that's being researched right now. And most importantly, we're going to do, as I mentioned, 3D mapping. The 3D model of the interior of the mine will be able to inform experts on whether or not this mine is suitable for conversion. So next slide. Yeah, so just wanted to talk a little bit about our prototype. We're doing long-term design and our prototype design concurrently so that we can learn from the prototyping process and let that inform our long-term design. On the left, you can see a photo of a testing event where we took the prototype into the basement of the mine where they have a wave tank. They have a pretty complicated camera setup that can accurately track the position in space, velocity, acceleration of the prototype. So we're probably going to be taking advantage of that in the future. On the right, you can see our electrical system. So central to our Raspberry Pi, which is the brains of our robot, we have a 6S LiPo battery, a inertial motion unit or IMU that has an accelerometer and a gyroscope that informs on the position of the ROV. We have 4 thrusters, 2 on the XY axis and 2 on the Z axis for controlling pitch and XYZ translation. We have a sensor for detecting temperature and pressure, which in turn tells us the depth of the robot. And we have a camera. So that's where we're at right now. Yeah, next slide. So yeah, goals for the semester, we want to modify our existing prototype so that we can have onboard localization and we can adjust to dynamic currents. We're going to be integrating our sensor technology. So those sensors I mentioned earlier so that we log that data and make it useful to us. We'll be integrating our user interface. We'll be testing in that same facility in the wave tank, and we'll be making long-term CAD drawings of the of our design. So yeah, that's my presentation.
Absolutely impressive. Geez,
Right.
is there anything your group doesn't do, Paul? My goodness.
I'm sure if we look for it, we can find something. We can't do everything. We have a lot of amazing students, but we are still limited in how many hours everybody can spend on doing things. So we do a lot, and we're having a lot of fun doing things. But yeah.
It's I think what ties all your work together is the making use of equipment in unstructured environments, or environments that are extreme environments, you know. Very interesting, very interesting. Thank you, everybody. It was really, really, I learned a lot about what you do. I always wondered what went on in those big trailers outside between our two buildings. And so with that giant liquid nitrogen tank on campus, is that to cool your sand off, or?
Yeah, so to simulate the lunar environment, we need to make it as cold or as hot as it can be out there. And so, minus 196 degrees Celsius is the temperature of liquid nitrogen. And so that's what we use to cool down the lunar sand, the lunar regolith, but also the equipment that has to function under those conditions as well. So.
Well, very good. So there, audience, you can ask questions by using the Q&A feature. And I'm going to leave it up to you guys to start answering questions and read them off, so that people can understand what question you're answering.
I'm looking through the questions here. I have a question about the last presentation here, Gabe. For the ROV, you mentioned fish. Are the fish in flooded mines, or is that for other survey areas?
I don't think I mentioned fish. We don't expect to see fish in the mines because there's no sunlight, no ecosystem down there. If there is an inlet from external sources, maybe that's where you're coming from, then it's possible we could see fish.
Indeed. Somebody wants to know where the wave tank is. Well, the wave tank is in the bottom basement of the main building here. And so it's a tank that was built specifically to be able to generate waves and look at alternative energy for harnessing some of the wave energy, for instance. And so it's down in the basement of the meme. And I always like to say we have the beach up on the 7th floor, and they have the ocean down in the basement. That's pretty cool. Now we just need to have a bar with drinks somewhere. Anyway.
Diane asks, how do students get involved in these different programs? And do you need computer engineers in your group?
A great question. Maybe one of you guys wants to answer. Brenda, maybe?
Yeah, so Lunabotics team, given that we have an entire team devoted to automation on our robot. So if a computer engineer wants to work more on the software side, you could definitely find something on our team as well as any of the others, I'm sure, or even the hardware side, getting sensors, different components to get involved with that. To get involved with Multiplanetary Innovation Enterprise as a whole, you just have to be a student at Michigan Tech. We start accepting students at the 2nd semester of their 1st year here at Tech, and you can enroll in it. Same way you would enroll any class, except I believe you need advisor approval, which I don't think Paul has turned down anybody yet. So it's really easy to get involved, and you get to choose which of the 3 odd projects you'd like to be on. And then we're very good about figuring out what your interests are and finding the best fit for you within a team as well. So if you are an upcoming student, can recommend getting involved. I've had a lot of fun with it.
Yeah, the only caveat to that is because you work in my research lab, I can only have U.S. citizens or U.S. persons, so green cards. So that's the only limitation because of ITAR and EAR regulations. And so that's not necessarily true for mine in general, but that's because you work in my research lab that restriction is in place. So. All right. See, here's another question about the trencher. How does the trencher not dig too much material out?
Yeah, so there's basically two different trenchers we're talking about. There's the one that we're going to put outdoors and the one that's in the vacuum chamber. So the one in the vacuum chamber is on like a precision motion stage that can move it left and right and soon up and down. So it's a very precise amount of movement that we know it'll be able to do. So no matter what the cutting forces are, it'll stay in exactly the same place where we put it. But outdoors, or on a real rover, that's a big concern because the cutting forces could pull you deeper into the regoliths. You have to make sure that your drivetrain is very well controlled to make sure you don't dig too much and get it stuck in the ground.
Along those lines, how deep does it need to go typically?
Yeah, so we don't really know yet. The Viper mission, which is launching the next few years, will basically put a drill down into the moon and categorize how deep we need to go in order to find the resources that we're looking for. Because we only know that there is water on the moon. We don't really know how it's distributed across the depth. It might just be at the very surface, or it might be 10 feet down. We don't know yet, but we will find out. There's a lot of work going on in that area.
And a related question from Dennis is, did you test the digger in both vacuum and atmosphere?
Yeah, so that's a kind of a central part of our research papers that we're writing. We test the exact same system and the exact same configuration, basically with the DTVac turned on and with it just at ambient pressure. And what we do is we compare how the performance of it changes between atmospheric and vacuum. So if other people want to do research in this area, they can use atmospheric conditions only, and then use our correlations to find out potentially how it would perform in vacuum. And we haven't published that yet, but that's what our goal is. So we can help other people understand how it differs in vacuum, because it's very hard to get this large of a vacuum chamber on Earth.
Are any of you grad students, or are you guys all undergrads?
All undergrads.
And you're writing papers. It's just so
Yep.
impressive.
By the time I graduate, I should have 6 publications for an undergraduate student. And some of
you
that is
should become
also
a faculty member, get a PhD and become faculty.
I do also work for Paul's lab, so it's not just Trencher, but Trencher is one conference paper and one journal paper that'll have my name on it, which is far more than most undergraduate students have that don't go through this enterprise.
Yeah, I strongly believe the students should be credited for the work they do. So they get their name on papers for the work they do. So, but yeah, any question? I saw a question here. Somebody was asking if there's many first-year students on mine, and so the way the enterprise works is, as you're a freshman, the first semester you cannot join because you need to acclimatize and everything like that. So the second semester of freshman year, you can get involved through ENT 1960. And so we don't have many, but we do have some typically. I mean, usually 1, 2, or 3 per year. But of course, the technical knowledge at that point is somewhat limited because you haven't had a lot of classwork yet. And so what we're looking for is of course, passion to get involved. And second of all, being able to learn some of the skills, and whether that's machining, or maybe people have already done, let's say, first robotics in high school and they already know how to do a bunch of things. And so we're happy to have first-year students join the enterprise, as long as it doesn't cost you the grades in other classes because you're having too much fun in the enterprise.
Enterprise, we've featured Enterprise before, but I think it really distinguishes Michigan Tech from many other universities, because you get in these enterprise, in something like this. I mean, so each of you has been in this enterprise for multiple years, right? Brenda, how many years have you been on it?
I remember it was weird. This is my second year in the enterprise.
Okay. And Gabe? Okay. And Parker?
3 semesters in total so far.
Okay, wow. And you're like leading groups and things like that. It's pretty impressive. All right, we have a question from Don. In push, please explain the water flow. Where is water pumped to, and where would a turbine be located?
Yeah, I'll take this one. So In a push facility, for our design case, the turbine will be located in the main shaft. So it's easier to show with a picture, but in a mine, typically there's a shaft that goes all the way down to the bottom of the mine, and it's a straight, for the most part, shaft. And then there are levels that branch off from there. Not all the levels are flooded, so there is a significant amount of dry levels in the upper part of the mine. So the thought is you could have the pump or / turbine, same difference, near the bottom of however much water you can pump up, and then pump all that water into the upper levels of the mine. So
there's another question related to push here, in the sense that when exploring the submerged mines, do you expect to have any issue with particulate buildup on camera sensors from particles in the water?
yeah, that is something we've researched. It's looking like probably not. Most mines have been around long enough that any particulate matter has settled to the bottom. So anything in the any turbidity in the water will be caused by us moving around, causing changes, unless there's something like an underground river or something like that that's spinning dust around.
Bat poo.
In the dry section mostly.
All right. Carson wants to know, when are you going to get your own building? Well, I have no plans to build Paul a building, folks, but I agree, he deserves one.
Yeah, we're working on seeing if we can get support for a special test building that nobody else has in the whole world, as a matter of fact. So
All right. Well, see, Paul's got plans that his dean doesn't even know of.
we're making drawings right now so we can show the pretty pictures to you. So you can better imagine what this thing should look like. So we weren't quite
Yeah.
right ready to share this with the rest of the world, but that's okay.
I think somebody spilled the beans there.
It's all right. It's not really a secret, but it's not well known yet. So
Is that bar in the drawings, Paul?
is that what? The bar? No bar there.
No, not on a. All right, here's a question from Cade. And it's kind of related to how Michigan Tech is slowly planning on growth. And so the question is, I think, what the capacity of the mine enterprises are. And so maybe, Paul, you can take that, because I can see you have students in different teams. I mean, we just heard from the 3 teams that you have. Would you just add other teams?
Yeah, so there's definitely room for growth. The aerospace enterprise, to name one, has about 100 students, I believe, and it's a matter of how you organize the enterprise. And so we could add additional projects, but that comes also with more time from my end to have another project, another feedback that needs to be given. Another option is to have more students work on each project and have more sort of sub-teams. Like that's one thing that Lunabotics does, for instance. So they have, what, 5, 6 sub-teams, Brenda?
We have 5 sub-teams, yes.
Yeah.
Plus, oh no, 6 if you count system integration.
Right.
So.
Right, and so that those are groups that specialize in specific components or aspects of in this case, the robot. But for instance, for push, you could have more sort of the environmental team, and you could have more of a robot exploration team. So there could be different aspects that could be expanded within the projects as well. So there's a variety of different options available. And so we also do external sponsored projects. Like we had 4 projects last year. One of those was externally sponsored. And so those are typically 1-year-long projects, more traditional senior capstone design type projects. And then we do that project for a year with a group of students, and then next year maybe there's a different project, or sometimes none. So it depends on what projects are available and also what the students' interests are. So I've had in the past also had students define projects that they were interested in doing. They have to, of course, meet certain standards, but we can certainly discuss that as well. So there's a variety of different options and how we could accommodate more students within the enterprise.
Students, do you see any questions you'd like to answer? If so, just read it out and answer it.
Yeah, so somebody asked what the most common elements are on the moon, which I was really surprised when I learned this, but the most common element on the moon is actually oxygen, which makes up 40% of the moon. So unlike Mars, where there's a lot of CO2 and even water ice, on the moon, almost all of this oxygen is locked up in minerals like silicon dioxide or many other things. So in order to get this oxygen to a usable form for us from those minerals is a very complex and energy intensive process. So while there is 40% of the moon is made of oxygen, very little of it is easy for us to get to. The small amount that's in water ice for the most part, and methane and stuff like that.
And by the way, this is true for Earth minerals too. But
Yeah,
we have plants and other things that liberate that oxygen. So
it's a good thing we don't have to do this on Earth, because it'd be a lot harder than what we just breathing plant air.
right.
Gabe, do you see any questions you'd like to answer?
I do. So Dennis asked, follow up on the mines. You mentioned pumping it to higher elevation than gravity flow generates at times of need. For Ludington, we use the same turbines in both directions and excess generation capacity to run the pumps when demand is low. Are you envisioning separate pumping mechanisms or a similar setup? So Dennis, it's really cool that you work at Ludington. Didn't expect to see any reps here. We don't really, we're researching the push facilities. We're not designing it. I know I think it's the Alternative Energy Enterprise has made a penstock design, and we've reached out to them. We'll probably be reaching out more in the future. So it informs on our design, but
I think it also would largely depend on the mine itself, right? So some mines have different geometries and different shafts, and so you'd probably adjust the design to whatever the mine would accommodate, with minimal changes.
Your focus is on mapping the mine, and because I mean, like here in Houghton, I think they threw junk down the mine shafts toward the end. There's just a bunch of stuff down there. Brenda, do you see any questions you'd like to answer?
Yeah, I see one asking about the trencher teeth, if they're carbide or trencher, your trencher optimization system. Parker, that's yours. Never mind.
Yeah, so both Trencher and Lunabotics are rebuilding their excavation systems this year. Last year, they both used metal flat-bladed teeth, more or less. The Lunabotics ones had some points on them, but they're more or less just flat metal blades, aluminum or steel. The two-body wear, which is just the particles hitting the blade, it's not a huge concern compared to the three-body wear of regolith getting in bearings and stuff like that. And regolith is a granular material, so you don't need sharp points like you would with on Earth trying to cut through rocks or anything. It's basically just scooping up sand. So while the teeth are an important consideration and part of the research paper we're writing, there's no particular material constraints on them. They could probably be made of plastic even. So I don't know if they'd last long.
I know for the Lunabotics competition, we cannot use plastic purely because we have those giant gravel rocks hidden in the soil. So for us, that's a consideration. But again, the moon itself is different than what we have here to work with.
So we're coming up on the hour of 7, and I want to kind of begin to bring it to a close. So I'm going to ask students in the order of Brenda, Gabe, Parker, if you would like to make a closing remark, maybe a tip for an incoming student on how to get involved, or anything you'd like to add as a remark. From me, my closing, and then we'll end with you, Paul. But from me, I just want to thank the audience for joining us. I learned a lot tonight. Thank you to the entire team. And we'll see you next week. So closing remarks, Brenda.
Yeah, no, thank you all for coming. If you are a future student interested in getting involved with Enterprise, I highly recommend it. You learn a lot putting your hands on projects. And I think I've learned probably more in Enterprise than I have in some of my classes, which says a lot. And so I definitely recommend it. If you're a first year, try an Enterprise. If you don't like it, you can always switch. It's a great opportunity. And not only do you get technical skills, but you also get a lot of project management skills as well. And that's been a huge help to me as too. So try Enterprise.
Gabe, you're next.
Yeah. Again, thanks for coming. Yeah, I can definitely speak to what Brenda said, and that it's really helped me build up my resume and attract recruiters' attention. I think they really pay attention to soft skills like management and collaboration, sometimes more than they look at technical prowess. So yeah, definitely would recommend Enterprise if you're looking.
Parker.
Yeah, Enterprise has been really cool for me. In some ways it's similar to First Robotics, but you're not really publishing papers in First Robotics. It's really cool to be doing stuff that's more on the leading edge of what people can do. So all of these projects are very much out there, which you don't really expect to be doing as an undergraduate student. So you can get involved so early and learn so much in this program. It's been really cool. And there's a lot of opportunities to do even more stuff after you're done with Enterprise program.
Super. All right, Paul, you get the last word.
Well, first of all, thank you all. This was a very interesting session. Thank you all for attending. And if you have any questions, please feel free to reach out. I'm happy to talk for days about any of this kind of stuff. So it's a lot of fun. But more importantly, it's really a lot of fun to work with all the students. They're very talented. They're very motivated, and they do amazing things. And all that work that I do, really, it's them doing the work. I often do just mostly the paperwork. So all those accomplishments are really the students' accomplishments, and I'm very proud of all the accomplishments that they have achieved so far. And I think there are many more to come if I know the students. So looking forward to that. Thanks for having us, Janet.
You're welcome. Good night, everybody.
Good night.